welcome to Stat 310 lecture 12. So today we're going to wrap up chapter 8. So we spent quite a while on chapter 8. This is a very important chapter on detailing kind of key estimation procedures and what we can say about the properties of them. And in particular for the last two, and this will be the third lecture in a row, we're going to talk about maximum likelihood estimation, because this is a kind of a really important procedure that's very widely used in statistics. So sort of understanding that's very important. So in particular, we're going to talk about finding confidence intervals for theta hat ML. We kind of detailed that at the end of the previous lecture, but we're going to kind of do an example where we can kind of see that in action. Then I'm going to talk a little bit about the idea behind the proof of the asymptotic normality result for theta hat ML. I mean, this is not something you need to that you will be examined on, but I think it's a good thing to understand kind of where all the terms come from in the asymptotic normality results, and the proof kind of gives some idea behind it. And I won't be super rigorous. I'll kind of just give the main ideas and then kind of point to the textbook if you want to do more detailed reading. And then we're going to finish with a discussion of a lower bound, which kind of says that the idea behind it is that the maximum likelihood estimate is actually the best you can do in some sense, in an asymptotic sense. So that's how we're going to kind of finish wrapping up chapter 8, and in particular the discussion on maximum likelihood estimation. And then if we have time, I'll just kind of summarize the key findings of chapter 8. So let's kind of review a little bit of what we've seen in the last couple of lectures. So we spent quite a while on this maximum likelihood estimation. So the idea here is that you have n random variables drawn from some PDF or PMF indexed by this parameter theta, and your goal is to kind of estimate this theta. And the maximum likelihood procedure essentially just involves you taking the maximum of this sum of these log likelihoods. Remember, it was originally the product of the PDFs or PMFs, but you can rewrite that as the sum of the logs of the PDFs or PMFs, and that's been a very convenient way to do the calculations. And we've seen that the logs have been kind of important in a lot of the calculations and terms. And in particular, there's also this notion of asymptotic normality, which is really powerful because it allows us to say something about the distribution of theta hat ML, and then also use that to find confidence intervals. So in particular, when we introduce this notion of Fisher information, which is related to the double derivative of the log, you can show that if you scale by n in this Fisher information, then you get asymptotic normality. So you can use the normal approximation and get confidence intervals, whether they be 95% or any other percentage, just kind of using the normal table and then just standard notions of and then just what you know about finding confidence intervals when you know the asymptotic variance. Okay, and in the previous lecture we did a lot of calculations for how to find that Fisher information in various cases, just two derivatives of the logs and then taking expectation of that random variable. So let's begin with an example where we put these ideas into practice. So we're going to use an example from the previous lecture again, but put them together to find a confidence interval. Okay. So remember that we defined this PDF, which is indexed by this parameter theta, and it has this form theta x to the theta minus 1, where theta is bigger than or equal to 1, and x is between 0 and 1. Okay, and so we have a data set x1, x2 up to xn, where n equals 100 and the sum of the log is negative 150. Okay, so this is what we know about this data set. And so the question is, find theta hat ml and 95% confidence intervals using theta hat ml. Okay, so remember that we've kind of done a lot of these calculations already, so I won't repeat them. I'll refer you back to lecture 11 where we looked at this distribution in quite a bit of detail and calculated the necessary quantities. So we've actually found that theta hat ml is equal to okay, so that was our theta hat ml. And so in this case, that's just and so that's going to be 150 over 100, and that's 1.5. And you can check that that's bigger than 1, which is the range of the theta that we had. So this is our theta hat ml. And to find 95% confidence intervals for theta, so we know that the 95% confidence intervals take this form where you use the maximum likelihood estimate as the center of your distribution. Okay, so we need to, obviously for this, we need this Fisher information. So recall that I of theta is 1 over theta squared. And here alpha is 0.05. So what you get if you look up a z table is just 1.96. So just to be more explicit about that, (1.96) is the point where you see 0.025 is the error in the right tail, which is alpha over 2. So okay. Okay, so because we have that I of theta is 1 over theta squared, then we can kind of say that 1 over square root of I of theta hat ml just is equal to theta hat ml, which is very convenient. And so we end up with, if we plug in 1.5 here, okay, and so our 95% confidence interval is our approximately it's going to be about 1.2 to 1.8. Okay, so you can check that as well. But so this gives us kind of a, with 100 data points, we can get somewhat reasonable accuracy in terms of how well we can estimate this theta. But so this is just the procedure of how to find. So the general procedure for finding confidence intervals is pretty simple. It's firstly each step in itself takes work, but in terms of how to put the steps together, it's relatively simple. So we first need to find theta hat ml, which is obviously a lot of what we spent a lot of time figuring out how to do that. Then we need to find I of theta, and then plug in theta hat ml, so to get I of theta hat ml. And then you just need to find z alpha over 2, which is, just look up z table for that. And so we have this, very general procedure that, not only gives us a point estimate, but also gives us some confidence intervals. So okay, so it kind of ticks all of the components of our framework. I mean, we start with the general the data, then the statistical model with the parameter theta, then the statistic or estimating procedure, which is the maximum likelihood procedure, and then we have the way to get the asymptotic distribution through this Fisher information, and then the way to calculate the 95% or any other confidence interval you might be interested in. Okay, so what I'll talk about now is just the idea behind the proof of the asymptotic distribution of theta hat ml. So the result is, we've already used the result, is that okay. And so where does, a natural question is, where does this come from? Okay, and it's covered, the proof is just a lot of analysis, but I kind of just want to give you an overview of the basic ideas, just so that, you might look at that and think, where on earth did these come from? Like the Fisher information seems like this sort of odd quantity that's really pulled out of thin air. But it actually, does sort of come from, some sort of an intuitive idea that we'll go into shortly. So page 274 to 278 in textbook kind of goes into this proof in a lot more detail than I will. But I'm just going to kind of outline the basic points. So, and yeah, the main thing to kind of get out of this is just to get this idea of why the log of the likelihood is such an important sort of function and quantity. And also just to, remind yourself of quantities like what the Fisher information is, what the log likelihood is, and so on. So this should be kind of an insightful, potentially an insightful thing as well. So the first thing we're going to do is remember that we defined the log likelihood in this way as okay, so note that L of theta is a random variable because it's a function of n random variables. Okay. And the first thing we should note is that, we know that theta hat ml equals argmax of theta, L of theta, right? And so what that kind of means is that if you take, I'm going to use this prime notation for the derivative, you can kind of say then that L prime of theta hat ml equals 0. So L prime is the first derivative. Okay, and so, what we can then do is we're going to use Taylor approximation, and this is where we're going to kind of see the second derivatives come in. So we know that L prime of theta hat ml, if you imagine doing a Taylor approximation, so around theta, so this is an approximation, sorry, this is not exact, this is an approximation. So this is just the and so this is the first order Taylor approximation, and you can kind of show, and I'm not going to do this rigorously, but you can show that the other terms aren't significant when we look at the asymptotics. So therefore we have that L prime of theta hat ml, on the one hand we know that it's 0, and on the other hand we know that it's approximately L prime of theta plus L double prime of theta. So we already have things that are starting to look a little bit promising, because we can rearrange this because we have this equality equal to this thing equal to 0. It's negative L prime of theta over L double prime of theta. Yeah, sorry that these L's look a little bit like E's, but yeah, they should be just script L's. I'm going to try to be better about that. Okay, so then we're going to now introduce this square root of n, because that's going to be there as well. Okay, and for scaling reasons, I'm just going to re-express this as I'm putting the negative on the denominator, and then I'm just going to have, okay, so now we know that expectation of 1 over n, L prime prime of theta, or the negative of that, is just equal to the Fisher information. That's the that's kind of the definition, right? So we know that negative 1 over L prime prime of theta converges to I of theta. This is by the law of large numbers. So again, we're being a little bit hand wavy here, but you can say that this is approximately 1 over square root of n L prime of theta, and then on the denominator we're going to have I of theta. And so what I'm going to do now is just bring over one of the I of thetas, because we kind of know what the answer should look like. It should look like this on one side. So we're going to take one of the square roots here, and then we're going to get a square root of I of theta here. And so what we're going to do is to hopefully show that that this term should converge to normal 0, 1. So that's kind of what we want to show now. And the basic idea is as follows. So note that 1 over square root of n L prime of theta, that is 1 over square root of n times the summation I equals 1 n of d log okay, and you can rewrite that as square root of n times 1 over n. Okay, and so then so there's a few interesting kind of properties of this random variable. So this is a random variable here. The first thing to note is the expectation of this is actually 0. There's I'm going to refer to the proof in the book because this is again quite a technical result, but it's just you can show through some calculus that this expectation is 0. But then also we have that the variance of this random variable is equal to the it turns out that this is equal to the Fisher information, and then this again, the proof of this is in the book as well. Okay, so what that means is that by the CLT, what we know then is that square root of n times 1 over n minus the expectation of over the square root of the variance of that thing is going to converge to a normal 0, 1. Sorry, I'm running out of space here, but that's a normal 0, 1. And then we know that this expectation is 0, so we know that this is 0, and then this is I of theta. And so then we have that square root of n times d theta, and then we already have kind of this this term in the denominator times square root of I of theta, that thing's going to converge to normal 0, 1 by the CLT. So therefore, we have that square root of n of, and then there's this I of theta here. Theta hat ml minus theta converges to normal 0, 1. Okay, so again, the main thing to kind of take out of this is just the high level points of the proof and kind of where this comes from, because I sort of don't really like this theta result where it just seems like it's pulled from thin air. So this is just an idea of where all the important terms come from. Okay, so this is essentially where the Fisher information comes from. It's sort of this variance of this d log of this log of the the derivative of the log function. Okay, so that was quite technical. If you want sort of a more rigorous version of this proof, you can go to pages 274 to 278 of the textbook, but you don't really need to know the proof of this result. I just wanted to show it to you to give you a clearer idea of what's going on. Okay, so we're going to do another example to kind of break up the technical, sort of that technical proof that we saw, and we're going to kind of return to an example that we kind of haven't seen for a while, which is this normal distribution, where we kind of know what's going on, but I want to apply the maximum likelihood theory to the normal distribution to see what we get out of it. So here we're assuming that mu, which is the population mean, is our parameter of interest theta, and sigma squared is some fixed known constant. So we're treating sigma squared as fixed and known, and we're going to let mu be the parameter of interest. And so okay, so what we're going to do now is just essentially just repeat this procedure again, just so that it's clear in our mind what to do for each step, and then we're going to calculate the Fisher information in this case and find confidence intervals, and we can compare to see if they're any different or very similar to what we've kind of already done. So the first thing to note here is that okay, so this is the PDF here. Sigma is a known constant. This is the PDF for the normal. Here x is between negative infinity and infinity. And so if we take logs like we have before, then we end up with okay, so this is what we get when we take logs of everything. And for part one, so I believe we've already done this calculation, but I'll try to quickly go through it again here just to remind everyone. And so that's so this is our L of mu here, and so we want to take the derivative L, and that should be 0. So if you take the derivative, the first two terms disappear and you just get that this just becomes 1 over sigma squared. This thing should be 0, and that you just get that mu hat ml equals the sample mean. Okay, and so this is, we already found this, we already discovered this, but I just kind of gone through it again. So we kind of don't expect anything too surprising because we found that this sample mean is in fact the maximum likelihood estimate. And so, but then, we can ask the question, do we get exactly the same confidence intervals? And you sort of hope that we do, but let's check that by finding out the Fisher information. Okay, so if we look back at the log of the so we have the d log which we've already calculated. Sorry, this is d mu. That we know is okay, so we get that this is the let me check that that's correct. It's so you get a negative for the for what's inside, and then another negative. So I believe it should be actually this. So it should be 1 over sigma squared xi minus mu. And then if you take the derivative again, you should just get negative 1 over sigma squared. So therefore, okay, and so for part 3, where we're looking for we're looking for confidence intervals. So we know that square root of n okay, and then we also know that, so this means that so because mu hat ml is x bar, we just get exactly what we kind of expect here, which is, what we already knew, which was a CLT. And in fact, as we know from earlier, this is in fact an exact result. So the 95% confidence intervals that we get are okay, and so this is not, this is again just another sanity check to see that we've done something that is consistent with what we already know. So we've seen examples, some which give us things that we already know, and others that give us something new. And this is one, and so this again is just an illustration of how this general procedure works of first finding the maximum likelihood, finding that Fisher information and then finding the confidence intervals. And so I've kind of gone through those basic steps, again. Okay, so the final thing we're going to cover in chapter 8, and also related to maximum likelihood theory and the estimation procedure, is, we've kind of talked about how it's a widely used procedure. A natural question to ask is, can you really do any better? The notion of better or worse is a little bit more of it's more of an art than a science in real data types of applications. But what you can do, which is done in theoretical statistics quite a bit and mathematical statistics quite a bit, is you kind of formulate some optimality criterion and see if your estimate is kind of optimal or can be beaten with respect to some estimates. So the question we're posing is, can we do better than theta hat ML? Or another way to think about it is theta hat ML optimal in any sense? So this is going to lead to the Cramer-Rao lower bound, which is going to kind of address that question to some degree. Okay, so here Fisher information kind of magically appears here again, and that's going to be important because that's going to tell us something about the variance of any unbiased estimate. So what we're saying here is that now we want to kind of look at any possible estimate you could come up with. So any estimate or a statistic is just any function of the data. We have to make sure that it is in some way related to we have to make sure that it is in some way related to theta. So we do that through a pretty widely known property of unbiasedness, and you've kind of seen that unbiasedness has come up as a kind of a nice property of estimates to say in expectation you kind of get the truth. So this theta hat is not necessarily the maximum likelihood estimate. It is any estimate that you could come up with, but it's unbiased. Then the Cramer-Rao lower bound basically says that the variance of theta hat is bigger than 1 over n times I of theta, this Fisher information. So let me write that out properly. So remember that I of theta was this negative double derivative of the log of the PDF or PMF. So what we're really saying in words is that for any unbiased estimate, typically small variance is a good thing. Its variance is at least 1 over n times I of theta. So the Fisher information kind of acts as this sort of lower bound to say that you can't really come up with a procedure or estimator that's going to do better than that if you want your estimate to be unbiased. And one thing to note is that true for all n. So this is a finite sample result. So what we're going to do for the so what we can say for the maximum likelihood procedure is that asymptotically you can't do any better. So this is a little bit different than saying that for any choice of n you can do better, because that's very, very hard to say. That because for specific n, you can often kind of construct weird estimates that might do better than maximum likelihood. But what we can say here is that the maximum likelihood kind of does better than any other estimate asymptotically according to this criteria. So note that for theta hat ml, E of theta hat ml, so this is that's going to go to theta as n goes to infinity. So it's asymptotically unbiased. This follows from the law of large numbers. And then we also know that asymptotically that okay, so we also know that that's true. So so therefore the variance of theta hat ml converges to 1 over n times I of theta as n goes to infinity. So by Cramer-Rao lower bound, theta hat ml is so amongst all asymptotically unbiased estimates, theta hat ml is the estimate with the smallest variance. So we can kind of conclude theta hat ml is asymptotically optimal. Because we're kind of using the notion of optimality here to say that, the estimates with the, the smaller the variance, kind of the better. Because if smaller variances typically mean that you can get tighter confidence intervals. And so we're saying that the maximum likelihood estimate is actually the one that does best in terms of amongst all estimates asymptotically. So this is really sort of one of the reasons why maximum likelihood is widely used. So this is why it's kind of one of the most widely used procedures, because we can get good confidence intervals, and it turns out that asymptotically you kind of, and so for large n you really can't do much better than that in the sense of trying to minimize the variance. Okay, so that's pretty much all we're going to cover from chapter 8. So we're going to finish just with a quick summary of everything we've covered in chapter 8, because there was a lot to take in, and I kind of want to go over it again and put it back in the context of our framework. The statistical framework that we have here. So we have our data, which is this x1 through to xn, which this is coming from our sample, and then the distribution. So the thing that chapter 8 did that chapter 6 and 7 didn't do was that we were trying to have general parameters. Chapter 6 and 7 really focused on like population mean and population variance, but here we're trying to be as general as possible. So we assume that these draws are independent, because that kind of gives us these nice properties, and then we also, so theta is the parameter of interest. And then we spent a fair amount of time talking about two procedures that were general. So we had, one here was the method of moments that we spent 1 or 2 lectures on, where we kind of said that so if you plug in mu to be the expectation, you can write theta as a function of mu, and then the method of moments estimate was kind of simply just plugging in the sample mean. So to find theta hat mm, we just simply plugged the sample mean into theta hat mm, and there were also higher order, like if you wanted to go to 2 parameters, you could use 2 moments and so on, but most of the examples we saw involved 1 moment. So the main the only real sort of mathematics we had to worry about here was first how to calculate the expectation, and then how to find that g, which typically involved inverting a function. And then we spent more time on maximum likelihood because the procedure at first might seem a little bit more complicated, but gave us some, as we saw, some pretty nice properties. So theta hat ml is so we sort of talked about you just multiply the PDFs. And you could also kind of write it out in terms of logs, which often made the calculations much easier, and we sort of saw the value of looking at logs. And so you typically had to do this through differentiating and setting things to zero. So differentiation was certainly a very widely used tool when we were talking about maximum likelihood estimation. And then we talked about distribution of statistics. So So for the theta hat mem, we didn't spend a lot of time talking about the distribution because we couldn't like there was it was hard to really pin down a general type of procedure to do that. In other courses you can and you do, but we didn't really do that here. But we found that in specific cases, if g is a linear function, so for example, for like the Poisson, your theta hat mm was just x bar. Same with the normal. Then in that case, you can kind of just use the CLT to get an asymptotic result. But for maximum likelihood, the last two lectures we've spent a fair bit of time talking about this. So for theta hat ml, we get this very nice general result that and this is, I'm putting in brackets for most cases because, you did need some conditions that usually hold, but not always. We have that converges to normal 0, 1. And so, you have that this approximate distribution and then for the fifth component, which really sort of was about using the like to do some analysis. So use to do some inference, so rather than just come up with a point estimate, also try to come up with some notions of confidence intervals. So using ML, we came up with this kind of general this pretty good to we could find any confidence intervals or any symmetric confidence intervals for theta. Okay, and so we saw today that to find these confidence intervals, it's really about putting together all of the little things that we've learned. So firstly, how to find the maximum likelihood estimate, which we spent a good sort of lecture going through some examples on how to do that. We spent about half a lecture in the previous lecture talking about how to find the Fisher information for various examples, and so that's kind of another very key and important calculation that you're going to need to be able to do. And so again, that just involves differentiation and taking expectations. And then once you have the maximum likelihood estimate and the Fisher information, finding the confidence intervals is a pretty simple task, I'd say, or it uses ideas that you should hopefully already know at this point. Okay, so that's kind of a summary of what we've covered in chapter 8. So I think this is a good point to stop. And then in lecture 13, we're going to kind of move on to chapter 9, where we talk about hypothesis testing. Okay, thanks very much.